Okay, welcome back. So today we are starting chapter 2. This is limits. And the goal today is to start the limit section and provide you with the tools that you can start working on different limits. I'm not planning to move much in this session, but these are the things that I have to make sure that we have in place before we move on. So I will start with limit. So when it comes to the mathematical precise definition for limit, this is something that we won't do it in this class. You have to actually take another higher level class to be able to go through what's called epsilon delta definition. We won't go through it. This is just an intuitive way. We will introduce intuitively what does it mean. You already seen some parts. And the hope is that it would just give us good start so that we introduce the tools. So let me start with the definition, intuitive definition. Doesn't work. OK, first thing, very important thing. When you're trying to find limit, you're working with functions that are defined around a point. So let f be a function defined around point A, but not necessarily at A. So this is one of the key points, that when we work with the functions, with the limit of functions, we really don't consider if the function is defined exactly at that specific point or not. When I say around that point, what I mean is that, OK, so at A, it doesn't need to be defined. But there is an open interval that includes A, and, well, function is defined on that interval. Why do we need that? So let me fix the notation. We say f has a limit, or the limit L, as x approaches to A. Well, hopefully you're not expecting me to repeat this whole thing anytime I want to write a limit on the board. So that's why we fix a notation denoted by lim fx as x approaches to A is equal to L. So we say that function has limit as x approaches to A, or we write it mathematically like this. Lim subscript x approaches to A, f of x is equal to A, if the values of f can get arbitrarily close to L if we get sufficiently close to A, or if we can get sufficiently close to A. Or I shouldn't have written V if X can get sufficiently close to A. Well, I need to write this to make sure that we do it one time for the class. But what I mean is that you decide how far I want to get close to that number. So, UL, you send me your request that I want the values of the function f to be this much close to L. Then I have to be able to fix small or close enough x values to A such that any x value in that closeness will give you the value which is this much close to L. Or even more intuitive is that I can get as close as I want to L by getting closer to A. So here, so I can, for example, in this case, I can fix this much close to X. Any value in this part of X will give you something in that interval. All these things, you can turn it into a little bit machinery of, okay, evaluating limit is not about evaluating the function. It's about studying the trend of values of function when x gets closer to A. It's not evaluate. It's not about one value. It's about trend of values as they get closer to A. Well, in example, we will see, so let f of x be this guy. Use the table of values. To find here, or to understand the trend, to find the trend of limit of f of x as x goes to 1. What do I mean by this? So this is the only mechanical example. This is the only example, the mechanical example that I will do in this class for limit. But what I mean by that is this, that aren't we trying to see what values of what number the values of f gets close? How about then let's fix something? Let's say, okay, x at 1, I want to get close to 1 using x values. And then I want to look at what values the function will achieve, will obtain. Yes? And then we will try to find a pattern. Are these getting closer to a number or not? One thing to note here, this is very important, and that's one of the things that you should take home today, that when we are studying limit of function, as x approaches to A, we are not talking about f at A. And in some cases, such as this one, the function may not be defined at A. So in this case, the function actually doesn't have any value at 1. Why? Because 1 makes the denominator 0. But I can look at the values close to 1. For example, is 2 close enough to 1? It's close, but we want to be able to get closer. Okay, how about this, 1.1? Yes, it is good, but I want to get closer more. Well, even more. Even more, yes? So I won't be able to show everything in numbers here. I'm just trying to mechanically show you what we are studying. But even this number, when it comes to limit, is not close enough. No number is close to another number enough, because you can get always small closer and closer. That's why when it comes to limit, this is just a very basic method of finding limit, and that's almost not the worst one. We will never use it, okay? So here are the values when we are approaching to 1 from the right. How about from the left? Maybe I start from 0 and then go to 0.9, then maybe 0.99, 0.999, and so on. Okay? Now, I will give you 40 seconds, more than enough. Try to evaluate the function in these values, and let's see what is the trend of the values of function when we are getting closer to it. Go ahead, please. 40 seconds. You probably need to share this time with your friend. One part you do it, the other part your friend does it, and you don't need any calculator, I can promise you. Okay, if I plug in 2, what do I get? When I plug 2, what do I get? 2? 3, okay. When I plug in 1.1? 2.1. Are you using calculator? Did anyone calculated these ones without calculator? Okay. I will hear from you. So this one they already said. What do I get if I plug in this one? Yeah? 2.01. Okay, 2.01. Back there. What did you get if you plug in this one? Yes, yes. 2.001. And if I do the same things here, I'll get here 1, 1.9, 1.99, 1.999, and so on. Yeah. Why it's possible without calculator? This is simply because when you're trying to evaluate this function at values other than 1, you can do this thing. You can factor upstairs and downstairs here. And I can cancel these two. This is x plus 1. Oh, wait a minute. You taught us last week that anytime you cancel, you have to be very careful, because canceling sometimes kills some information. Can anyone tell us why in this case it's not going to kill any information? Yes, please.
The information that we're losing is that x cannot be equal to 1.
When we are trying to cancel, the only thing we have to make sure is that that factor is not 0. Yes? And here, when we are trying to find the limit, we never care about the value of the function at 1. So anything but 1, I'm trying to evaluate this function, but around 1, but not at 1. Anything else you plug in, x minus 1 is going to be not equal to 0, so I can cancel it, and I can get this one. And that's why you're seeing that, oh, it's 2 plus 1, this plus 1, this plus 1, this plus 1, and so on. OK, so that's the table of value. Now, we have to study a little bit carefully. Sometimes you will see the pattern. Sometimes it's not that easy. But in this case, do you see any number that these guys are approaching to? Or they're getting closer to? It is 2, yep. And that's where we just write the limit of this function as x goes to 1 is equal to 2. Any questions, any comments for me before? Well, you can find some other examples. Actually, I would suggest to see some examples from the textbook that does that uses the table of values just to give you the right feeling of what we are doing there. But before we move ahead, I want to make sure that you've seen examples for which the limit does not exist. So examples of limits that do not exist. Yes, do you have a question? Yes. So one of these examples, which usually is not easy to do if you don't know the graph, this is when you're trying to find limit of sine 1 over x as x approaches to 0. See, one thing you have to note here, as for this function, again, the function is not defined at 0, because I cannot plug in 0 there. 1 over 0 doesn't make sense. But you should see this way, that when you reverse when you reverse x to 1 over x, you are sending interval 0, 1 to interval 1 to infinity, and interval 1 to infinity to interval 0, 1. And when you're doing that, basically what you're doing is this, that the graph of sine x, you remember that periodic graph, you have to take this part from 1 to infinity and squish it all into here. And the squeezing will go more as you get closer to 0. There were infinitely many up and downs, yes? Now I want to put them all in one place. What will happen is something like this. Okay, nice. It gets closer. Still goes between -1 and 1. But then as we get closer to 0, this guy gets crazier and crazier, up and down, between -1 and 1. Never stops. Remember, there are infinitely many up and downs. Now everything is squished over there. And as we get closer, it gets even crazier. The other side will go kind of the same story. Oh, I did go up a bit more than what I needed. So this, nothing is changing, always between -1 and 1. Now, remember that when we are finding limit, we are trying to see what values, what are the values of the function f getting closer to as we get closer to that 0 here. As we get closer to 0 from either side, the function oscillates even faster between -1 and 1. There is no number that they're specifically getting closer to. They're always, this thing is getting up and down, up and down, up and down, up and down, even getting faster and faster. That's why this limit is one of does not exist. What is DNS? Does not exist cases. And again, without the graph, it's not easy to see that. Another example is this guy. I will ask you, I will give you 1 minute. You probably need to talk to a friend sitting next to you. First, sketch that graph of that function, absolute value of x over x, and then try to see if you, based on graph, if you can understand why the limit at 0 does not exist. Your 1 minute starts now. Go ahead, please. Seconds left. Okay. What is the graph of this function? Can anyone? Yes, please.
When x is negative, it's always -1. When x is positive, it's always just 1.
So you're saying that this absolute value of x over x is 1 if x is positive. If it is negative, it is -1, yes? Well, one way to see this is just use the definition of absolute value. Absolute value is piecewise defined function, yes? When x is positive, absolute value will give you x. And when x is negative, it will give you -x. That's the definition of absolute value. But now here you're dividing it by x. You're dividing it by x. The only change you have to be careful here, since you're dividing by x, you cannot include 0 in the domain. So it's either +1 or -1. At 0, it's not defined. And that's the graph. And by the intuitive definition there, you should now see when we get closer to 0 from the right-hand side, no matter what value, positive value you plug in here, you're always going to get 1. So function values, when we are using positive x's, are always 1. When we are using negative x's, they're always -1. And remember, we are trying to find, I slided the board on that one. We are trying to find one number that the values of function getting closer to. These values are getting closer to 1 and -1. There's no way that they're getting closer to one value. They're considering two different things. So it's not going to be a good limit here. And this is another case of the limit does not exist. We will see more cases as we go on, but to start with, I think it's good to see at the beginning that, yes, you have these cases in hand and you can work with it. Any questions, any comments here? Do you have? Yeah, you good? Okay. Yes, please.
The limit of sine again.
So for sine 1 over x, you have to understand the limit, the graph. The graph, well, I ask you, please, when you go home, use whatever tool you use to graph functions. 1 over x, when you get closer to 0, this thing starts oscillating. And the oscillation always goes from -1 to 1 and comes back. Yes? As we get closer to 0, this is jumping between these two things even faster. Means what? Means that it's not getting closer to anything. It's always jumping between these two numbers that are far from each other. Yes? That's the intuitive way of saying it's not, the limit does not exist. Any other questions? Yes, please.
You have the limit.
Sorry, well, cosine of 1 over x is going to be very similar to that. Very similar to that. It doesn't have a limit when it is cosine 1 over x. The graph is a little bit different, but basically, again, we have this oscillating case between 1 and -1. Before I move to the limit laws, I just want to make sure that everyone in the room has answered the poll which is open on our account, on the iClicker account. Yes? Just make sure, please, because I'm going to close it, and today, if we have enough time, I'll post a question, but this will be basically our attendance mark.
Hi.
Pardon? Yes, the hi, yes. Say hi, that's it, yes. Well, that's, I already teach. This is now you should know it. Yes. Yes, I still see more answers are coming in. Please complete that, and then I'll start the limit laws. Yes, please. Cos of 1 over x has very similar graph. What happens is, well, I mean, the only difference would be that both of them will go like that. That's the only difference. The rest, the oscillation is still there. Does not exist. I see around 250 students in the class. I only received 215 answers. Do it. You will lose the attendance mark. Okay. These ways of dealing with limit is boring. It is not practical. And most of the time the expense is too much. You have to spend time and energy and CPU time to either graph it or do this thing. We need tools. We will learn at least 3 groups of tools that will help us to evaluate limits without going through these pains. The first group of these things, which I'm hoping to finish it today, is limit laws. You have to look at these things as the tools or power tools, and you want to learn how to use them. What are limit laws? I'm assuming that let f and g have limit as x approaches to a. So that's our assumption. I usually don't, so in the books, usually limit laws, they don't include these two things. And these two, I'll write 0. 0 cases, we don't call them limit laws. These are just important limits that you have to know how they work. Limit of a constant as x approaches to a. Our understanding of the graphs of the constant function, it stays horizontally. No matter what you give, fit in, it will give you back c. So the values of function is always equal to c. So the trend is also c. Limit of constant as x approaches to any number always exists and is equal to that constant. The second thing is limit of x as x approaches to a. You can either use the graph, or you can see this as a tautological thing, because as x approaches to a, x will approach to a. There's nothing more there. That's just like tautologically trivial thing, yes? These are two things that we will get back to it and we will use it, but limit laws are actually starting from this point. We call either sum law or difference law. What does it say? It says that you have two functions which have limit as x approaches to a. Now, if I cook up a new function from these two guys, by adding those two functions, remember combination? This is sum. If you create this new function, then your new function is going to have limit, and you can actually evaluate that limit by knowing what is the limit of the first summand and what is the limit of the second summand. So limit of sum is equal to sum of limits. Limit of sum is equal to sum of limits. The difference will go the same way. So if it is minus here, this will be minus as well. Product also goes the same way. So this is sum law, difference law, product law. So instead of maybe writing 1, I'll write 1 to 3. So 3 laws there. There is another one. This is the fourth one. It's called constant multiple. So what does it say is this, that if your function is product of a constant to your function as x approaches to a, that constant will come out. Indeed, this is an easy version of product limit, because if the first function is constant, limit of constant is that constant, and that's how this works. So limit of constant times function, the constant will come out, and limit of the function. Well, we did sum, subtraction, product, constant, multiple. What else is left? Quotient. Quotient law. This is the important law. Oh, why I'm writing it there? Not there, here. Quotient law says that limit of the quotient of two functions that has limit as x approaches to a. I'm sorry, I am writing it very low there, and I know that the people back there are not seeing it very well. So I'll rewrite it over here. Limit of f of x over g of x as x approaches to a is limit of f of x as x approaches to a, limit of g of x as x approaches to a. That is wrong. Well, it's almost nice. That will work most of the time. But you will notice that that law that I wrote, the way I wrote it up there, won't work, and that will create lots of work for us, and we will soon see those ones, hopefully tomorrow. But what is the problem? What could go wrong here? Can anyone? Yes, please.
The limit of g as x approaches a could be 0.
The function g may not be 0 around a, but when x approaches to a, it may become 0. So the limit of the denominator could be 0. This is only true when limit of the denominator exists and is not equal to 0. Only then. And again, this is very, very important point. We will get back to it. We will fight for it. And you will see the useful limits will happen when the limit of the denominator is 0, actually. So the limit of the denominator is 0. We will deal with it more often than just when it is not 0. Any questions, any comments before I write down some examples and you try to evaluate some of those? Before it is too late, I can write the power law, and this is called quotient law. There is power law, which says if you have limit of f of x to the power n positive integer, as x approaches to a, this is going to be the limit of f of x as x approaches. So limit and power work nicely. Here n is positive integer. And when it is rational power, so I have nth root of f of x as x approaches to a is nth root of limit of f of x. No, this time, this is good. There are cases that we have to be careful when n is even, then we have to make sure that limit of f of x as x approaches to a bigger than or equal to 0. Remember the restriction for even roots. We cannot put negative number in. That limit, that condition is not going to generate much problem for us. And that comes from the fact that the function itself, when we write nth root of f of x, it means that it is going to be always bigger than equal to 0. Otherwise, I could not make sense of the left-hand side. And if it is not bigger than equal, it is always bigger than equal to 0. So that means that you will hear that limit will also be bigger than equal to 0. So that condition over there is not going to create much trouble for us. Okay, so let me write down some examples. And we have only 5 minutes. Let's go ahead and try to complete these two limits. The only thing I'm going to ask you, which will happen later on in the course as well, that I'm asking you to go step by step. And in each step, you have to write what limit law you're using to be able to perform that step. So it will take a little bit of work, but I want you to, you remember, writing is everything here, yes? So if you're using a tool, you have to let me know that which tool you're using. Go ahead, step by step. I'm using quotient law, I can use it, and this is what will happen. Then next step. And go ahead and please do it now. Okay, I'm turning off the poll. I'm hoping that everyone has answered that question. Remember that this is about the attendance. Okay. Okay, let's do this one. I'm using sum or difference laws. And the first step will be, this is x squared minus limit of 3x as x approaches to 0 plus limit of 2 as x approaches to 0. Then I can apply here, I can apply power law. So this will be limit of x to the power 2 as x approaches to 0. Here I'm applying constant multiple. This will be 3 limit of x as x approaches to 0. And this I'll leave it. So see, in the case of polynomials, I can follow their laws and turn everything down to only 2 limits. Limit of x as x approaches to something, limit of a constant as x approaches to something. And in this case, this will be 0 squared minus 3 times 0 plus 2, which is 2. Yes, please.
So would it be okay if I factored it and then used the multiple law?
Sure, yes, yes. For this one, I need the first law I want to apply there is I want to get the quotient law done. But what I should do should do first to be able to use the quotient law is that I have to check that the limit of the denominator is not 0. So here, the limit of x plus 1 is limit of x plus limit of 1 as x approaches to 1. And that is 1 plus 1, 2, and it is not 0. Yeah? So I can use the quotient law. So here I will go all the way here. Quotient law, and I can say limit of x squared plus 2x minus 1 over limit of x plus 1 as x approaches to 1 and x. And repeat the steps that I have done. So few steps. Here, this will boil down to 1 squared plus 2 times 1 minus 1, and here will be 1 plus 1. And that is 2 over 2, which is 1. This process, I'm not going to ask you to repeat this process because of the fact that I'm going to write now down there. It's called direct substitution rule for the polynomials. But what I want you to learn from this writing is that whenever you use a tool, you have to cite it in some ways. And the direct substitution rule says, I'm sorry, I will write this and then you can go. Direct sub says that if P and Q are polynomials, then limit of Px as x approaches to a. Polynomials you can break down always like that, and at the end you will get exactly nothing but evaluating that polynomial there. So for the polynomial, since this moment on, you can always write direct substitution rule, done. For the rational functions, also you can do the same thing with one difference, that here you should make sure that the denominator doesn't give you 0. Well, you come back tomorrow, I will provide more tools, we will study a bit more examples, and you have to start working with the tools. Have a great day and see you all tomorrow.